Hello and greetings. My name is Syed Moiz Hussain, and I'm here to currently present you my work on the complex engineering problem for the course of mechanical vibrations ME315. So the complex engineering problem was regarding the mathematical modeling of a car suspension system. So I'll begin by first presenting the problem statement. The problem statement was to model the suspension system of the car passing over the disturbance of amplitude A. So the road is being treated as a disturbance with an amplitude A, which is shown in the figure as you can see. And there were certain design limitations and requirements. As first, the system was supposed to be a 1 degree of freedom system, and the moving mass of the system was also to be considered, and the base excitation was also to be taken into account. Moving on, I'll first begin by explaining the physics of the suspension system. So basically, what a car suspension is, it's an essentially a damped spring in short, which produces an opposing force when the spring is compressed. So basically, an automobile car suspension system is based on two components. First is the spring, and second is the damper. What spring does, spring sustains the weight of the vehicle, and dampers, on contrary, oppose the spring movement. What they do is dampers dissipate the energy and prevent them to bounce without control. So in short, an automobile suspension system of a car is excited harmonically by a road surface through a shock absorber. So the suspension system of the car can be modeled by a linear spring in parallel with a viscous damper. Uh, the system can be modeled by considering the system to be excited by the motion of its support, and all this system forms a base excitation or support motion problem in which the base is following a motion because of the road within certain amplitude. Okay, so moving on this whole system, an energy analysis can be performed in which both the mass of the car and the mass of the wheel is taken into account. The mass of the wheel is shown by the wheel is shown in this figure by a circle, and the mass of this car is shown by a rectangle. So in this energy analysis, we'll take the mass of the car and mass of the wheel both into account. So by when we perform the energy analysis, we imply that the energy conservation will be taken into account, which means during the entire oscillation of the suspension system of the spring, the maximum kinetic energy of the entire system includes the mass of the car and the mass of the wheel, will be equal to the maximum potential energy of the entire system, which again includes the mass of the car and mass of the wheel. So this is the principle of energy conservation. So when we talk about the principle of energy conservation, the kinetic energy of the system will include the translation energy of the wheel and the car, because wheel and the car are both moving linearly. So their translation energy, and it will also include the rotational kinetic energy of the wheel because the wheel is rotating. So using this energy analysis, an effective mass of the system is also evaluated. Its significance will be seen in the next slide. So as you can see, the mathematical modeling of what I just said. First, the this principle, the energy analysis applied, in which the principle of energy conservation is applied, in which the maximum energy is kept equal to the maximum potential energy. Yes, so the maximum kinetic energy is kept equal to the maximum potential energy. And as you can see, the maximum kinetic energy includes the kinetic energy of the car, which is translating, the kinetic energy of the wheel, which is also translating, and kinetic energy of the wheel, which is rotating. So the kinetic energy of the wheel is kept as 1 upon 2 j over r square and x dot squared, which is the velocity, and you can see the rest of the kinetic energies. So when this is evaluated, you can see an effective natural frequency is calculated, from which an effective mass is evaluated, which includes the mass of the wheel, the mass of the car, and this part is due to the rotation of the wheel. So you can see small m represents the mass of the car, w represents the mass of the wheel, j is the polar moment of inertia of the wheel, and r is the radius of the wheel. Okay, so moving on. We'll first begin our analysis. After that, we'll begin our analysis by applying the Newton's second law, which equals F is equals to ma in simple. So as you can see here, ma, which involves F is equals to ma. So ma is the acceleration here, as you can see, x double dot. And the two forces involved in this analysis are the spring force and the damping force. So in spring force is k x minus y. So as you can see, x is the displacement of the car, of the mass of the car, and y is the vertical displacement of this base, which can be seen as this rectangle. So the net displacement is given as x minus y. So this is the spring force, and the damping force is given as c into x dot minus y dot. So after applying this Newton's second law, which includes both the forces, spring force and the damping force, and the mass is given as the equivalent effective mass, which we found out in the previous slide, which is the mass of the wheel, the mass of the car, and this part is due to the rotation of the wheel. And we have summarized this as an equivalent or effective mass, as you can see in this notation. So we have just solved this, and additionally, you can see in the bumping of the road, we have treated it as a sinusoidal function. We have assumed that the trend it follows is of the nature a sine omega bt, where a is this amplitude of this wave, as you can see, and this we have assumed it follows a sinusoidal pattern, and we have just simplified by keeping the y values here, and by changing these c, the damping coefficient, the k spring constant, into z eta omega n, which is a natural frequency, as you can see. So this is the final differential equation, which gives us the response of the spring suspension system. As you can see, these two are the forcing functions. This function is because of the spring, sorry, because of the damper, and this function is because of the spring. So we will begin the solving the differential equation which we found out in previous slide. So we will begin by solving first this homogeneous part, and you can see on the slide the homogeneous part is written here. As you can see here, the forcing function are removed, and instead of those forcing function we have written a 0 here. So we have started by assuming that the solution is of the form a e power lambda t, and then we have kept this function into this function, and we have formed a function in terms of the lambda, and then we have found the two values of lambda, lambda 1 and lambda 2, as you can see here in terms of zeta and omega n, which is the natural frequency. Now we have assumed that damping ratio to be less than 1, which implies that lambda must be between 0 and 1. So we have opened this function into, we have taken -1 common here, and which implies -1 as j, which is iota, the complex part, which makes it the complex function. So we have rewritten lambda 1 and lambda 2 in this form, and then we have substituted this back into this initial equation with two lambdas. So we'll get this result, lambda 1 and lambda 2. Next, to simplify this function, we have introduced another frequency omega d, which is equals to omega n under root 1 minus zeta squared. And then we have substituted this into this function, and this function is simplifies in terms of omega d. And then we have taken this common out, and this equation further simplifies. So moving on. Now what we have tried to change this exponential function into a sinusoidal function. So for that we have used the Euler's identity, which says that e power of theta into j, the complex, is equals to cos theta plus j sine theta. So what we have done is applied this identity here, and this function, as you can see here, is simplified into some sine part and some cos part, and some exponential part is still present here. So what we have done here, we have further reduced these constants, the capital A1 and capital A2. We have applied the sign identity in which we have used the Pythagoras theorem, in which capital A1 squared plus capital A2 squared is equals to capital A, and phi is can be given as the inverse of tangent inverse of A2 over A1. And this further simplifies the identity into this single identity, as you can see here. uh, this is the simplified version. Okay, so further moving on to the boundary conditions, we have assumed that at time t is equals to 0, our car is at a certain distance of x naught, which is given by a sine phi. So using the equations from our course book, equation 1.38, which implies that a must be equal to this constant, a must be equal to this expression, and phi must be equal to this expression. So we have kept we have assumed that at t is equals to 0, our car was at stopped. So at t is equals to 0, the x naught was 0, which gives us a is equals to v naught over omega d. And finally it also gives us that phi is equals to 0. So this equation has been further simplified into this simple equation, which gives us the homogeneous result of the homogeneous response of this equation, which we saw on the previous slide. So moving on, we'll be moving on to the particular solution. So the particular solution will be treating these two forcing functions separately. So the first forcing function is because of the damping, because of the damper. So we have taken this response from the book, from our course book, directly, and we have written it here. So this will be given as this. And for the second forcing function, which is due to the spring, it is given as this. And these two equations are taken from our course book directly. So what we'll be doing now, we'll be adding these two particular solutions to get the total particular solution, which we'll be seeing in the next slide. So as you can see here, we have added the two particular solutions to get the total particular solution. So as you can see here, we have added these two solutions here, and then what we have done here is we have taken some things common out, and the form turns out to be this form. And then what we've done here, we have using this identity a cos omega t minus phi is equals to b sine omega t plus c cos omega t, where b is 2 zeta omega b and c is omega n. And from the Pythagoras theorem, as you can see on this triangle, a becomes this, a is equals to this expression. So this equation, these two cos and sine terms can be simplified into a single cos term with the inclusion of another angle theta 2. So as you can see, this particular solution has been simplified. Two separate particular solutions have been combined into a single particular solution, and theta 2 is given as this angle. So we have obtained our final particular solution of the differential equation, which we saw on the previous slide. So moving on, the total solution will be given by the homogeneous part plus the particular part. We'll be adding these two solutions to get our total solution, which will be the solution as you can see on the slide. So this represents the total response of the suspension system that moves on that bumpy road with a certain amplitude, a bumpy road that was modeled using the sinusoidal function. So this whole function represents the response of that car that moves on that jerky or that bumpy road. So we will now be moving on to the design analysis part. We will now be taking certain values which we have found from certain relevant resources. We'll be starting from K, which is a spring constant that the suspension system provides. So we have taken the equivalent stiffness is 4 exponent 4, which is a reasonable estimate for a spring stiffness constant of a car suspension system. Then for the damping of the suspension system, we have taken as 20 exponent 2. And for the mass of the car, we searched the internet, which is 1007, which is the mass of a small average passenger car. So this is an estimate, and this r is the radius of the tire wheel, which is also the radius of an average passenger wheel tire, a passenger car wheel tire. So this is an average value. And finally, the mass of the wheel is taken as to be 12 kg, which is also taken from relevant internet resources. So we have started by first evaluating the polar moment of inertia using the radius of the wheel. And then we have moved on to calculate the natural frequency, which we found using the expression which we found on the very beginning using the energy analysis. And we have substituted these values into it, and we have found omega n. Then subsequently we have found the damping coefficient zeta. So we have, you can see here, which turns out to be 0.1156x, which is less than 1, which implies that the system is underdamped, which proves our initial assumed hypothesis. And then moving on to the base frequency. So we have found this base frequency in terms of the car velocity. So car velocity, as you can see, v is in we have assumed it in kilometer per hour, so we have applied the relevant units to get it into radian per second. So we have found an expression of base frequency in terms of the velocity of the car, and then we have substituted this velocity as 20 kilometer per hour to get the frequency of the base. So moving on to the analysis, we have found theta 1 and theta 2, which were necessary to further simplify our response equation using these expression as you can see on the screen. and then we have found omega d, and then our amplitude, which was given in the problem statement as 0.01, and then we have substituted these values into the response equation which we found on the previous slides. So you can see these values I have substituted here. So this gives us the total response in terms of these numerical values which we can process in the coming slides. So as you can see, this is not in terms of some arbitrary expressions or constants. Instead it's in terms of some constants which is specifically for my type of car suspension system for which I took, for those values I took. So it's only relevant for such suspension system, for my suspension system. So moving on, I have plotted this equation into the MATLAB, as you can see here, and obtained a graph of the solution. So you can see the relevant code here. It's just a simple code of plotting the function, and the so it can be seen here. This represents the displacement of the car. The initial jerky displacement is due to the jerk on the road, the sudden jerk, and then as you can see, the motion becomes smooth, sinusoidal, which was assumed to be the sinusoidal, which was assumed to be the nature of the road, in which we assumed in the response. So as you can see, it becomes perfect sinusoidal. The response, the graphical solution. And further, one more thing can be seen. Our boundary conditions are also satisfying. At time t is equals to 0, the displacement can be seen here to be 0, and the maximum displacement of the car is around 75 centimeters. So moving on, we have provided an additional insight into this analysis by providing an energy dissipation in damped vibrations, was our car suspension system. So what we have done here, as you can see, this was our response of our car suspension system, the displacement function, as you can see here. Now we have taken the derivative of this function to find the velocity. Now next, what we have done here is we have found the potential energy of the suspension system using the expression half kx squared, in which we have substituted the x from this function x, and k is from our previous slide, which was 4 exponent 4, and so this can be seen as an expression of potential energy in terms of t, which can be plotted as which you will be seeing in the next slides. And we did the same for the kinetic energy of the system, in which the mass we have used is the equivalent or effective mass, as you can see this expression here, which we found in the previous slides. And then x dot is the velocity, which we found over here, the derivative, and we have substituted this. So we found an expression of kinetic energy also in terms of the time t. So we found the expression for both the potential energy and the kinetic energy. Next, what we did here, we plotted these two equations onto the MATLAB. MATLAB, as you can see here, the first equation is this of the potential energy, and this equation is of the kinetic energy. We have plotted these two equations, and third equation what we plotted is the sum of these two kinetic and potential energies. And what you see here is the code of what I wrote on the MATLAB to plot these three equations. So this is the response that I got. As you can see here, this red graph represents the sum of the kinetic and potential energies. The green graph represents the kinetic energy, which reaches the peak value here, the green graph, and you can see the blue graph represents the potential energy. As you can see, at time t is equals to 0, the potential energy is 0, but kinetic energy is maximum. And as you can see, eventually with time, the energy of the system decreases because of the damper into the suspension system. So this is the response which provides an additional analysis with respect to the energy point of view. So that is all from my side regarding the necessary project. I believed I fulfilled all the necessary requirements for this complex engineering problem. Thank you so much.